Hello and welcome to video 8. The topic of today is H-inf control design in Julia. And I have a Jupyter notebook up here and we have the agenda for today. We'll first talk about what is the H-inf norm and why would we like to minimize it. Then we're gonna solve a simple H-inf control problem. We'll talk about the extended state space type. That is a special kind of state space object that helps you do this kind of control design. And then we solve a more custom H-inf control problem. So first of all, what is the H-inf norm? Here I load the control systems package and the plotting package, and I create the simple transfer function P. Let's see, let's clear all outputs first. All right. Here we have our transfer function, and then I plot the border plot. And we see that the transfer function has a sharp peak here. And I have also called the function H-inf norm here of this P. And I plot the horizontal line corresponding to that. And we see the H-inf norm corresponds to the peak value of this transfer function. And that's indeed what the H-inf norm is. It's the peak magnitude of the in the border curve. If we would have calculated the H2 norm instead, it would be the integral here under the curve instead. So when we solve an H-inf control problem, we're essentially trying to minimize the peak of some transfer function. And what transfer function do we want to minimize? If we look at this system here, this is what I call an extended state space system in the control system package. But consider for now the system P. It has two sets of inputs, W and U. They might be, W might contain several different signals here, and the same for U. And then it has two sets of outputs. So W is some kind of external input, something that the controller cannot influence. So that might be references or noise, measurement noise, or input disturbances and stuff like that. And Z are the things that we really care about. So something that we want to make small. So for instance, the control error, we want to make that small. But it can also be the control signal. We want to make the control signal small also typically. U on the other hand is an input that the controller is allowed to modify. And Y is the output of the system that the controller has access to. So these are the measurements that these are the outputs that we can measure. And the interconnection of P and K here, the way it looks here is called a linear fractional transform. And P here, I call it an extended state space object. And the difference compared to a regular state space object is that we have partitioned it so that we distinguish between Z and Y and between W and U. All right, so a very common cost function to minimize in H-inf control is some kind of a weighted version of the sensitivity function. So the sensitivity function, we call it S, and maybe some weighted form of this sensitivity function, the controller times S. So this is the amplification of a measurement noise, and we typically want to keep that small. So if we change K so that the peak gain of this transfer function here is small, then we get perhaps a desirable closed loop performance. So this is perhaps a bit abstract, this block diagram up here, but we can make it more concrete. So here we have another block diagram with a controller K and a process P, and we have an external input. So D here is some kind of output disturbance, and our outputs are this here E signal. So that's the output of the plant, and then we apply some weighting function and we get E. But we also have the control signal going through another weighting function WU and produces UW here. So these are exactly those two weighting functions here. So the H-inf control problem in this case would be to minimize the transfer function between D and these two outputs. All right. So the first example we'll consider is a DC servo. So that's just an electrical motor. And we have the dynamics of the system here. So I can create that system as a transfer function. It's a very simple first order transfer function. And then the goal is to select those weights here, WS and WU. So for frequencies where WS is large, it means that we must have a small sensitivity function for this norm to be small. So we can select WS to shape how we want S to look. So if we want S to be small, we select WS to be large. And to help us do that, we have a function called makeWeight. So I can execute this cell, and we see that I plot the WS here. So makeWeight takes a gain for low frequencies, so something large. And then it takes a middle frequency, and then it takes a gain for high frequencies. So we see that it goes from a gain 10 to the power 5, and then it goes down to a half, and the middle frequency here is 0.5. So this is our sensitivity weight, and the weight for the control signal output, we just set it to constant 1. We can also select the weight for the complementary sensitivity function. We usually call it T, but in this case we don't bother with it, so we set it to an empty array. All right. Now we have created these weighting functions, and now the next step is to create this system P here. And that's perhaps a bit messy. So we have WS and we have WU, and we have our original plant transfer function. But then there exists a helper function called H-inf partition. So here we pass our plant model and our weighting functions. And the result of that is this extended state space type. And we see that this type has an A matrix, just like a regular state space, but then it has two different B matrices corresponding to the external inputs and the control inputs. And it also has two different C matrices. So these are the controlled outputs that we call Z, and this would be the measured outputs that we call Y. And then of course it has 4 different D matrices here. Then there is a function called H-inf assumptions that we can call to see if we satisfy all the assumptions of the H-infinity control design procedure. And it gives us a warning, and it says false. It says that this matrix does not have full rank. And it violates one of the assumptions from the paper here. And the problem here is that our plant model has an integrator, okay, and that's not allowed. So what we do is we define a small epsilon here, and we modify the plant transfer function to move the integrator slightly into the stable region. And once we have done that, we can call H-inf assumption again, and we see that all assumptions are satisfied. All right. So now we are ready to synthesize the controller, and we do that by passing our extended state space system P into the function H-inf synthesize. And we can also set a relative gamma that just, if we set gamma rel to 1, we are designing an optimal controller. If we set it to slightly more than 1, we design a slightly suboptimal controller, but there is usually a good reason to do that. It makes it slightly more numerically robust. So we do that, and that returns a controller K and the final norm that we achieved. So we want gamma, the resulting gamma, to be as small as possible. And in this case, we reached a value of 3.18. All right, so now we have a controller. We have our extended state space system. Now we can call H-inf signals to get a number of sensitivity functions that we might want to plot. So we get the closed loop system from disturbances to controlled outputs, and we get the sensitivity function, the noise amplification here, and the complementary sensitivity function. And we can pass those into the function called specification plot. And here we have that plot. So this is perhaps a bit messy, but we're going to break it down. In blue, solid line, we have the sensitivity function. It starts low for low frequencies, just like we wanted. And then it goes up, it has a small peak here, and then it levels out at 1. And in the blue dashed line, we have the inverse of the weight function for the sensitivity function, scaled by gamma. All right. And the reason is because for a single input, single output system, we can interpret this as an upper bound of the sensitivity function, the inverse. Remember, we make the weighting function large if we want the sensitivity function small. But for SISO system, the inverse just corresponds to this bound. So we see that this bound is tight for low frequencies, but then it's not tight for higher frequencies. And in red, we see the transfer function controller times sensitivity function. So that's the amplification of measurement noise. And we see that it's low for low frequencies. And then it reaches the bound here for medium frequencies. And then we have high frequency roll off. And the green curve in this case, we didn't have any weighting function for that in our control design problem. But the function here looks okay. And if this complementary sensitivity function would not look good, for instance, if it had a high peak or something, then we could include a weighting function also for that and minimize that as well. But in general, the solution here would be a trade-off between all of these objectives that we have specified. It's impossible to make them all infinitely small. If we try to make one smaller, the others will in general get bigger. So this is a design procedure that we can use to try to make a good trade-off. All right. So in general, we might want to penalize a more complicated signals and transfer functions. So here we have, in the top, we have a very complicated block diagram, but we're going to break it down. So we have a controller K and a plant P. And we can consider a lot of different external inputs to this closed loop system here. So we might have a reference, and we might want to perform some scaling of the reference. We might have some input disturbance, dW, and we might have output disturbances, dO, and we might have some measurement noise. And for each external input, we might want to have a weighting function that shapes the frequency response coming from this input to the output. And we might also have a number of different outputs that we care about. For instance, we might want to perform a weighting on the output of the plant and call that E and penalize that. And we might want to penalize the control signal output like we did with some weighting. We might also want to maybe penalize the control error here. That's also fine. I haven't drawn it in this picture. But in this example that follows now, we're gonna penalize the H-infinity norm of this transfer function. So we want to have the output sensitivity function, and we want to perform a weighting on the input and the output of that. So WD, so this would be the transfer function from DO to E, all right, with these two weighting functions. And then we want to penalize the transfer function from DO to U here with this weighting matrix. So all of the others will remove. So here I have redrawn the block diagram with only the ones we are interested in. So we're going to select these three weighting functions. So we penalize the complete transfer function from this disturbance to this output and this output. All right. So that would be very similar to what we did before, but now we do it in a more manual way. And to do that, I create what's called named state space systems. So here I take my transfer function or the transfer function we had before or a similar one, and I create a named state space system. I call the system P. All right, and I do the same for my weighting matrices. So in this case, this weight for the sensitivity function, I'll just use the plant system, the plant model for that. And the reason is that the plant has a resonance, and this will allow me to suppress that resonance by giving it a high weight there. And I give it the inputs and the outputs some name here. So we see the input to this sensitivity function weight is this signal, and the output is this signal. So here the input is called Y and the output is called E. And then similarly I select the weight for my control signal output, so this weight here, The input to that, I call it WU, and the output is UW, this signal here. And the same for WD here. It takes a signal DO as an input and produces a signal D. Right, so it corresponds to this. And we see here that it produces a state space object, but it also has these names for the different signals. And then I create a summing block. So this sum block says that Y is the sum of D and the PY. So if I don't, here I didn't provide any names for the outputs of P. I just provided a name for the system itself, and then it will give a default name of PY. So this creates more or less this summing node here. I create a splitter, and this splitter corresponds to this junction here. So this signal goes both into P and it goes into WU. And it splits in two. And then I make a list of all my connections in the block diagram. So this connection is a list of pairs of symbols. So it says that this output goes to this input and so on. And it corresponds to all of these lines, all of these arrows in this block diagram. Finally, I indicate which are my external inputs and which are my external outputs. So the output disturbance and the control signal are external inputs. Actually, the control signal is an internal input. But if I provide it in the list of external inputs, it will remain an external input as well in the transfer function I get. So that's nice for plotting reasons later. And my external outputs is the weighted control error, the weighted control signal, and I also want to see the unweighted output of the plant. All right. Now when I've specified all my signals and all my connections, I can call the function connect. So I pass in all the systems I want to include in my block diagram, my list of connections, and my external inputs and external outputs. And that creates a large named state space system with a lot of signals internally. But to create this extended state space system that knows which are the inputs we care about and which are the inputs the controller can, which are the inputs that are external and which are the inputs that the controller can affect. We call the function partition, and we specify that the controller can access a U, can perturb the plant through the signal U, and it can measure the signal Y. And now we get this extended state space that have two different B matrices and two different C matrices. Right, we can ask, are the assumptions of the H-infinity synthesis satisfied? They are. Then we call the H-infinity synthesize function, and we get a cost function value gamma. It's very small in this case, so it seems that this problem was easy. Then we can form the linear fractional transform, LFT. So that is, sorry for scrolling here, we form this system here. So we have our extended state space system and we have the controller we computed. And when we call LFT, we get that feedback interconnection, and then we plot a Bode plot of that. So here we have the Bode plot from the external disturbance appearing on the output, DO, to the scaled output. All right, and we have this transfer function from DO to the scaled control signal. But this is perhaps a bit unintuitive to look at because we have this scaling applied here that we selected, and that scaling we selected just to shape the frequency response. What we're maybe more interested in is the unscaled gang of 4. And we can access the gang of 4 with the function called gang of 4, and we can plot a specification plot. So here we see the sensitivity function in blue. And indeed we have a sharp downwards, kind of a notch here for a particular frequency. So we have suppressed something here, and this comes at the cost that we need quite high control signal gain for these frequencies here. But we have high frequency roll-off, so this is probably an okay design. If we didn't like the fact that we had a high peak here in the controller transfer function, we could increase the weight for that transfer function and push it down. All right, so connect back to the beginning. What have we done? We have looked at what the H-infinity norm is. It's the peak magnitude of a transfer function. We also looked at why we want to minimize it. We solved a simple H-infinity control problem. Then we looked at the extended state space system type that corresponds to this P here, where we know a distinction, a partitioning between outputs that we want to minimize and outputs that we can measure, and inputs that are external that we cannot influence with the controller, and inputs that we can influence with the controller. Then we selected weighting functions and solved the H-infinity control problem. All right, so the documentation for this is available in the Robust and Optimal Control Package documentation. So there is one example called Mixed Sensitivity H-infinity Control Design, and that corresponds to the first simple example we looked at. So mixed sensitivity just refers to that we penalize a combination of weighted sensitivity functions. All right, so this tutorial goes into more detail than I did during the video here, and solves the same problem. And then there is one tutorial called General H-infinity Design that does the second example. So it builds this block diagram, and it goes into detail how to form all the connections and so on, and solve that problem. All right, thank you for today.